when the locations of humanity's greatest ancient monuments are plotted correctly, not on flat maps, not through myth or folklore, but on a true spherical model of the Earth, something deeply unsettling appears. Structures built by civilizations that never met, never spoke, and never shared oceans fall along the same mathematically precise great circles, invisible paths that cut cleanly through the planet itself. These are not ley lines, not superstition. They are geodesics, the shortest possible paths across a sphere used today by satellites, aircraft, and GPS systems. Paths no ancient culture is supposed to have known how to calculate globally. So the question forms: how could civilizations separated by thousands of years, vast oceans, and incompatible worldviews place monuments along the same hidden geometry of the Earth? This is not a story about lost magic or ancient myths. It is a problem of mathematics, of probability, of satellite data and statistical anomalies. We are not here to declare answers, but only to follow the evidence where it leads, because some patterns are too precise to ignore and too dangerous to dismiss. Before we ask who may have built this pattern, we must first understand what the pattern actually is.
The Earth is not flat.
This is not a metaphor nor a philosophical statement, but a geometric reality that quietly governs everything built upon it. Every civilization that has ever existed has lived on the surface of a sphere, whether they understood that fact or not. And on a sphere, geometry behaves very differently than it does on a sheet of paper. Straight lines do not remain straight. Parallel paths eventually meet. Distances deceive the eye. What appears random on a flat map can become ordered when viewed correctly. To understand the mystery ahead, we must begin with one fundamental concept: the Great Circle. A great circle is the largest possible circle that can be drawn on a sphere. It is created when a plane slices directly through the center of the Earth, dividing the planet into two equal hemispheres. The equator is a great circle. Every line of longitude is a great circle. Any path that passes through the center of the Earth and intersects the surface produces one. Great circles are not abstract ideas. They are mathematical absolutes. On a curved surface, they represent the shortest distance between any two points. This is why they are also known as geodesics. If you stretch a taut string across a globe between two cities, it will naturally follow a great circle path. No shortcuts exist on a sphere. Geometry forbids them. This is why modern navigation cannot escape great circles. Commercial aircraft do not fly straight lines on flat maps. They follow curved arcs that appear counterintuitive on paper, but are optimal in 3 dimensions. Satellite orbits are calculated using geodesic principles. Undersea communication cables that span continents are laid along paths determined by spherical geometry. Even the signals in your GPS device are corrected for Earth's curvature, relativistic effects, and orbital motion. Great circles are not optional. They are imposed by the shape of the planet itself. The confusion arises because humans do not live on globes. We live on surfaces and we draw maps to make sense of them. Every flat map of Earth is a compromise. Some preserve angles, others preserve area. None preserve everything. In every case, something must be distorted because a sphere cannot be flattened without tearing its geometry apart. This distortion has consequences. Straight lines drawn on a Mercator map are often not straight on the Earth. Points that appear scattered can fall into alignment when projected back onto a globe. Lines that seem curved on paper may be perfectly straight in 3-dimensional space. The human eye, trained on flat representations, is easily misled. Modern geodesy exists to correct this problem. It is the science of measuring and modeling Earth's shape, orientation, and gravitational field. Using satellites, laser ranging, and atomic clocks, geodesists create precise digital models of the planet. These models account for Earth's slight flattening at the poles, variations in gravity, and tectonic motion measured in millimeters per year. When locations are plotted using these models, they are no longer abstract points on a map. They become coordinates fixed in a mathematically defined space. This is where patterns begin to emerge. On a flat map, ancient sites appear scattered across continents. They seem isolated, shaped by local geography, climate, and culture. But when their latitude and longitude are projected onto a true spherical model, relationships appear that are invisible in two dimensions. Sites separated by oceans and millennia can fall along the same geodesic path, not by artistic alignment, but by geometric necessity. This does not imply intention. Geometry alone can produce alignments. With enough points on a sphere, some will inevitably lie along great circles. The question is not whether alignments exist. The question is how precise they are, how many exist, and whether their distribution exceeds what random placement would reasonably produce. To ask that question honestly, one must first accept how unforgiving spherical geometry is. A deviation of even 1 degree on the surface of the Earth represents more than 100 kilometers. Over intercontinental distances, small angular errors become enormous. For multiple sites to fall within a fraction of a degree along the same great circle is not trivial. It is measurable, it is testable, and it is either real or it is not. Today, such tests are routine. Satellite Earth models allow researchers to project any set of coordinates onto a virtual globe and calculate angular deviation from any proposed geodesic. Statistical simulations can generate thousands of random distributions to compare against observed patterns. None of this requires belief, it requires data. What complicates the matter is historical assumption. Ancient civilizations are generally assumed to have had no concept of global geometry. They are credited with impressive local surveying, astronomical observation, and architectural precision. But global awareness of Earth as a sphere, let alone the ability to measure great circles across it, is considered a much later development. According to mainstream history, such understanding only becomes operational with long-distance navigation, accurate timekeeping, and mathematical formalism developed in the modern era. This assumption forms a boundary. On one side lies accepted archaeology, on the other lies impossibility. Yet assumptions are not evidence. They are placeholders for understanding, and they remain valid only until new data challenges them. The Earth does not change its geometry to accommodate human history. Great circles existed long before anyone named them. Geodesics guided the shortest paths across the planet long before they were calculated.
The question is not whether ancient people knew the mathematics. It is whether they could have recognized and used the geometry in some practical or symbolic way, even without formal theory. Navigation does not require equations to function. Observation, repetition, and long-term recording can reveal patterns that mathematics later explains.
For now, no conclusions are drawn. Geometry alone does not tell us who built what or why. It only tells us where lines can exist and where points fall when measured honestly. And this is where the story sharpens. Because if great circles are invisible yet mathematically absolute, and if modern tools reveal patterns that flat maps conceal, then the next step is unavoidable. What happens when the locations of ancient sites are plotted correctly, not as symbols on paper, but as points on a sphere that obeys the same geometry as satellites and stars? That question carries us forward. The idea begins not as legend, but as a research claim. It has a name, a method, and a measurable outcome. It is known as the Global Alignment of Sacred Sites hypothesis, and it does not propose lost magic, forgotten gods, or mythical energy lines. It proposes something far more unsettling, that when the world's most prominent ancient monuments are plotted accurately on a spherical Earth, some of them appear to fall along the same geometric paths with a precision that challenges simple coincidence. This hypothesis does not emerge from folklore. It emerges from coordinates. Latitude and longitude are indifferent to belief. They describe position on a rotating sphere using a universal reference frame. When these coordinates are treated correctly and projected onto a three-dimensional Earth model, a specific sequence of sites draws attention, not because of symbolism, but because of geometry. The sequence is striking in its scope: the Great Pyramid of Giza in Egypt, Petra in modern Jordan, Mohenjo-Daro in the Indus Valley of present-day Pakistan, Angkor Wat in Cambodia, the Nazca lines of southern Peru, Tiwanaku near Lake Titicaca in Bolivia, and finally, Easter Island, isolated in the vast Pacific Ocean. When connected in this order, these sites trace a path that crosses Africa, the Middle East, South Asia, Southeast Asia, the Pacific, and South America. The distance involved exceeds 16,000 kilometers. The cultures that built these structures existed in different millennia, spoke unrelated languages, practiced distinct belief systems, and had no known contact with one another. Yet when plotted on a sphere, they occupy positions that can be fit to a single great circle. This is not an artistic choice. It is a geometric observation. To understand why this matters, we must consider how such a fit is calculated. On a sphere, a great circle is defined by a plane that passes through the center of the Earth. Any two non-antipodal points define an infinite number of circles, but only one great circle passes through them and the planet's center. When more than 2 points are involved, the problem becomes one of best fit. Using spherical trigonometry, researchers can calculate the great circle that minimizes angular deviation across a set of coordinates. Each site's position is measured as an angle from the proposed geodesic. These angular distances are not linear errors. They represent deviations across a curved surface. Even a small angular difference corresponds to tens or hundreds of kilometers on the ground. This is where the claim becomes testable. In the global alignment of sacred sites hypothesis, the cited sequence of monuments falls within approximately 1/4 of a degree from the best fit great circle. Over intercontinental distances, this margin is not trivial. A deviation of 0.25 degrees corresponds to roughly 27 kilometers at the equator, and somewhat less at higher latitudes. Across 16,000 kilometers of travel, maintaining such proximity is geometrically restrictive. To put this in context, imagine throwing darts at a globe blindfolded. Some darts will land near each other. A few may line up roughly by chance. But for 7 widely separated points, all representing the most prominent monuments of their regions, to fall within such a narrow geodesic band is not what random scatter typically produces. This is where statistics enters the discussion, not to prove intention, but to test expectation. Earth's surface area is approximately 510 million square kilometers. The number of ancient monumental sites is finite, and their distribution is influenced by geography, water access, and population density. Random placement models can account for these biases by weighting landmass, latitude bands, and known settlement patterns. When such models are run repeatedly, they generate an expected scatter of points. Monte Carlo simulations are often used for this purpose. In principle, thousands or millions of synthetic Earths are generated, each populated with points matching the statistical characteristics of known sites. Researchers then ask how often a set of points aligns within a given angular threshold along a single great circle. The results do not produce a zero probability. Random alignments do occur, but they rarely involve the same specific category of sites across such distances with such tight angular clustering. The probability drops further when additional constraints are applied, such as monument prominence, cultural independence, and chronological separation. This does not mean the alignment cannot be coincidental. It means coincidence becomes an explanation that requires scrutiny rather than assumption. Importantly, the hypothesis stops here. It does not claim coordination. It does not claim shared knowledge. It does not claim a lost global civilization. Those are interpretations, not measurements. What the hypothesis establishes is a non-random spatial correlation that demands explanation. Geometry has revealed a pattern. History must now account for it or explain why it is misleading. This distinction is critical. Too often, discussions of ancient alignments leap from observation to conclusion. This research does not. It draws a boundary between what is measured and what is inferred. The phrase coordinated geometric network is introduced carefully and deliberately. It is not a declaration. It is a placeholder, a way to describe the observed pattern without assigning cause. Coordination may be cultural, environmental, navigational, symbolic, or illusory. At this stage, no mechanism is assumed. What makes this sequence particularly unsettling is not only its length or precision, but its composition. These are not minor sites. Giza represents one of the most precisely aligned monumental complexes ever constructed. Petra is carved into bedrock with advanced surveying evident in its axial design. Mohenjo-Daro reveals urban planning at a scale unmatched in its era. Angkor Wat encodes astronomical cycles into its architecture. Nazca spans kilometers of engineered lines visible only from above. Tiwanaku exhibits megalithic stonework with tolerances difficult to replicate even today. Easter Island stands isolated, its statues facing inward toward an unknown logic. Each site independently challenges assumptions about ancient capability. Together, their placement challenges assumptions about ancient perspective. This is why the hypothesis has persisted despite skepticism. It does not rely on mystical explanations. It relies on coordinates that anyone can verify and geometry that does not bend to narrative comfort. Still, caution is essential. The human brain is exceptional at pattern recognition, even when patterns are illusory. This is why statistical rigor matters. It is why error margins must be acknowledged. Coordinates have uncertainties. Some site locations are approximate. Ancient structures often cover large areas rather than single points. Best fit calculations depend on selection criteria, and selection bias is always a risk. Responsible researchers account for these limitations. They test alternative great circles. They randomize inputs. They publish deviations rather than hiding them. The alignment remains tight even when conservative assumptions are applied, but it is not perfect, and perfection is not claimed. What remains is a discomforting middle ground, too precise to dismiss casually, too incomplete to explain confidently. This is the space where genuine scientific mysteries live. The global alignment of sacred sites hypothesis does not tell us who built these monuments, why they were placed where they were, or whether any knowledge was shared across continents. It tells us something narrower and more dangerous to ignore. That when we stop flattening the Earth for convenience and allow its true geometry to speak, the distribution of ancient monuments does not behave exactly as expected. Something about the pattern resists easy explanation. And once one such alignment is identified, the mind naturally turns to the next question. Not whether it is true, but whether it is unique. If these sites truly share a single planetary geometry, then the next question is unavoidable. How many more follow the same rule? Once a single alignment is identified, it creates an unavoidable problem for interpretation. A lone great circle can always be dismissed as coincidence, selective plotting, or the product of human pattern seeking. But science does not evaluate claims in isolation. It asks what happens when the same method is applied repeatedly under consistent rules, without privileging one outcome over another. This is where the discussion moves from a line to something more complex. Researchers examining global monument distribution began asking a simple follow-up question. If one statistically notable great circle exists, are there others that emerge independently when different sets of sites are analyzed using the same spherical methods? When this question was pursued, the result was not a chaotic scatter, but the appearance of multiple great circles crossing the planet at different orientations. These are not arbitrary paths drawn after the fact. They are calculated geodesics derived from clusters of sites that independently minimize angular deviation. Each great circle is mathematically defined by spherical geometry, not by symbolic association. When plotted together, these circles do something unexpected. They intersect. On a sphere, any two non-parallel great circles intersect at two antipodal points. This is a geometric inevitability. What is not inevitable is where those intersections occur relative to Earth's surface features. When researchers mapped multiple great circle alignments associated with ancient structures, volcano chains, and known impact craters, they noticed that intersections were not evenly distributed across the globe. Instead, certain regions appeared repeatedly. This observation shifted the focus of analysis. Lines were no longer the primary unit of interest. Intersections became the focal points. An intersection represents a convergence of geodesics. In navigational terms, it is where multiple optimal paths cross. In geometric terms, it is a point of maximum constraint. If multiple independent alignments converge near the same location, the probability of coincidence decreases far more sharply than with a single line. Some of these intersection zones coincide with regions already known for unusual geological activity. Major fault systems, volcanic hotspots, ancient impact structures confirmed through satellite imagery and geophysical surveys. This does not imply causation, but it raises a critical question. Are ancient structures aligning to geography, or is geography biasing the apparent alignments? To address this, researchers turn to spherical clustering analysis. This method evaluates whether points on a sphere cluster more tightly than expected under random distribution models that account for landmass, latitude, and environmental constraints. The goal is not to find patterns, but to test whether clustering exceeds what randomness allows. The results have been mixed, and that is important. Some proposed alignments dissolve under rigorous testing. Others weaken when additional sites are included, but a subset remains statistically resistant. These clusters persist even when conservative error margins are applied, and even when site selection criteria are broadened to reduce cherry-picking. This persistence is what led some researchers to describe the phenomenon as a global construct of great circle alignments. The term is intentionally cautious. It does not claim intentional design. It describes an observed structure in the data, multiple geodesics, repeated intersections, non-uniform clustering. Crucially, this framework treats Earth as a single geometric object rather than a collection of isolated regions. Traditional archaeology often studies civilizations in geographic isolation, bounded by rivers, deserts, and mountains. Geodesic analysis ignores these boundaries. It treats every site as a point on a sphere governed by the same mathematical rules. This shift in perspective produces uncomfortable results. When sites from different continents are analyzed together, patterns emerge that are invisible within regional studies. These patterns are not obvious on flat maps. They only appear when Earth's curvature is respected. However, this is also where the risk of overinterpretation increases. The human brain is highly sensitive to intersections. It assigns significance to crossing lines instinctively. This is why statistical discipline becomes even more critical at this stage. Researchers must ask whether intersections occur more often near known sites than chance would predict. They must test whether similar intersection densities appear when synthetic random site distributions are generated. They must also consider survivorship bias. Only certain types of ancient structures survive to the present, and those structures are often built in geologically stable regions, which may already correlate with certain global features. When these controls are applied, the picture does not collapse, but it becomes narrower. The network does not include every ancient site. It does not form a perfect grid. It does not encode a simple geometric shape. What remains is irregular, constrained, and difficult to summarize, which is precisely why it resists simple explanation. One of the most misunderstood aspects of this research is the assumption that a network implies planning. It does not. A network can emerge from shared constraints rather than shared knowledge. If ancient builders independently favored certain latitudes, elevations, or geomagnetic conditions for reasons related to climate, agriculture, or ritual, similar placement patterns could arise without coordination. Yet some constraints fail to explain the full structure. Latitude preference alone does not generate great circles. River access does not produce intercontinental geodesics. Climate zones do not create antipodal intersections. Each partial explanation accounts for some features but not others. This is where the network concept becomes valuable. Even without answers, it reframes the problem. Instead of asking why one civilization built where it did, the question becomes why so many civilizations, independently, appear to have favored positions that align geometrically on a planetary scale. At this point, the hypothesis remains deliberately incomplete. No ancient map is claimed, no global survey is asserted, no lost technology is required. The only claim is that the spatial data, when treated with modern spherical tools, displays structure beyond naive randomness. This places the burden of explanation back on mainstream assumptions. Archaeology explains site placement through local factors. Geography explains settlement through resources. Anthropology explains monument building through culture. All of these remain valid. None are dismissed. But none were designed to explain global geometric coherence. The emergence of multiple great circles and their intersections does not rewrite history. It challenges the scale at which history has been analyzed. It suggests that some questions only appear when the planet itself becomes the frame of reference. This is the point where discomfort sets in. Not because an answer is known, but because the question becomes unavoidable. If the pattern is real, even partially, then someone, somewhere was responding to planetary scale constraints with surprising consistency. Whether that response was conscious, unconscious, practical, or symbolic remains unknown, and that uncertainty leads directly to the next problem. If this is a network rather than a line, then the final question is not where it is who could have mapped it, and how. The Nazca lines of southern Peru have long been viewed as a mystery. They are enormous figures etched into the desert floor, visible fully only from the air. For decades, speculation ranged from ritual pathways to astronomical markers to messages for gods who might observe from the sky. Yet closer study reveals a layer of complexity that exceeds all these explanations. At the heart of the Nazca Plateau are 5 primary centers, often referred to as radial points. From each of these foci, hundreds of straight lines radiate outward, crisscrossing the desert in remarkable patterns. These are not random scratches. They form a network of linear trajectories, each intersecting with others at carefully measured angles. The density of lines near the radial centers is highest, decreasing as they radiate outward. The structure is deliberate and systematic. What is particularly striking is the translation from 2 dimensions to 3. The lines themselves are drawn on a flat surface, yet researchers using spherical projection theory have demonstrated that they can represent great circles on a globe. Each primary radial line can be extended conceptually from its center across the Earth, passing through points that connect continents, ancient structures, and geological features. These are called primary great circles. Secondary lines emerge from intersections between primary lines or from secondary radial points. When projected onto a globe, these secondary lines also form great circles, but they are geometrically dependent on the orientation of the primary lines. In this way, the Nazca lines can be seen not as isolated artwork, but as a complex system of projections. Every line is oriented in relation to a larger framework. Even more remarkable is the interpretation of the geoglyph figures themselves. Many depict animals, plants, and other biota endemic to particular regions of the Earth. Some researchers argue that these are not decorative, not symbolic in a mythological sense, but functional. They act as geographic markers, specifying ecological zones across the globe. The condor, monkey, and spider may represent regions or climate types. Viewed in the context of the radial system, the figures provide a type of cartographic legend. They allow the observer to infer locations beyond the immediate desert. Aerial visibility alone cannot account for the precision or purpose of this layout. The lines are straight over kilometers, with angular deviations measured in fractions of a degree. This level of geometric fidelity is difficult to achieve without careful planning, surveying, and repeated measurement. Conventional explanations that they were designed for ceremonial walking or visual spectacle fall short when the lines are treated as three-dimensional projections rather than flat surface art. The concept of primary and secondary great circles introduces a hierarchy. Primary lines establish the skeleton of the system. Secondary lines create a network that links distant points, allowing the map to function on a planetary scale. Each line is geometrically anchored. When the radial centers are projected onto a sphere, the primary lines connect to points that are mathematically consistent with other known ancient sites. The secondary lines extend this network, filling in gaps and reinforcing the overall alignment. This perspective transforms the Nazca lines from a local curiosity into a potentially global instrument. The desert lines may encode a system of measurement or reference, where each figure and line represents a position, a vector, or a connection to a faraway site. They are no longer merely symbols or art. They are a structured record of knowledge about the Earth itself. It is this revelation that reframes our understanding of the lines. They may have been intended not solely for human eyes, but as a cartographic tool, a way of encoding spatial knowledge across thousands of kilometers. The precision of orientation, the deliberate placement of figures, and the radial network all suggest an understanding of scale and geometry that challenges assumptions about ancient peoples. If Nazca is more than a ceremonial site, more than an astronomical calendar, then it may be the earliest evidence of planetary mapping. Its lines, radial centers, and geoglyphs together form a system capable of representing the Earth's surface and the distribution of sites across continents. And if the Nazca lines function as a map, the next question is unavoidable. What exactly are they mapping? Among the great circles that span the globe, one stands out for its sheer symbolic and architectural weight. It has been named the Cyclopian Great Circle, a term coined by Jim Allison to describe a path connecting some of the most monumental and enigmatic ancient structures on Earth. The name derives from the cyclopean masonry that marks many of these sites, massive stone blocks fitted with precision so extraordinary that modern engineers still marvel at the craftsmanship. These structures convey power, permanence, and deliberate intent, yet their placement along a single geometric path adds another layer of mystery. The Cyclopean Great Circle is not a product of speculation. It emerged independently from multiple lines of investigation. Allison noticed the linear relationship empirically, mapping coordinates of ancient sites and realizing that several of humanity's earliest monumental complexes fell within a narrow geodesic band. He did so without using satellite projection tools or consulting prior research on the Nazca lines. Later, other researchers, using completely separate datasets and methodologies, arrived at a similar conclusion. This independent convergence strengthens the credibility of the observation. It is one thing to find a pattern once. It is far more compelling when the same pattern appears under scrutiny from distinct perspectives. Along this path, Cyclopean masonry is a recurring feature. The Great Pyramid of Giza anchors one end, a structure whose massive stone blocks weigh tens of tons and align almost perfectly to the cardinal points. In the eastern Mediterranean, megalithic constructions at Baalbek and other ancient Levantine sites echo similar construction techniques, though separated by millennia and culture. In South America, Tiwanaku exhibits gigantic stones, fitted with precision so exact that modern researchers note the absence of mortar and the impossibility of replication without advanced engineering knowledge. The repetition of Cyclopean techniques along this geodesic raises an unavoidable question.
Is it merely coincidental that some of the world's most technically sophisticated monuments align along the same great circle?
This alignment is not limited to construction style. It intersects with early monumental architecture centers that played pivotal roles in the development of urban planning, social hierarchy, and religious innovation. Mohenjo-Daro in the Indus Valley, Petra in Jordan, and Angkor Wat in Cambodia are all positioned within geometric parameters that connect to the Cyclopean Great Circle. Each of these sites demonstrates advanced surveying, architectural knowledge, and the ability to coordinate labor on a scale rarely achieved in antiquity. Their positions along this circle suggest that location selection may have been informed not only by environmental and cultural factors, but also by geometric principles on a planetary scale. From a scientific perspective, the independent rediscovery of this circle by different researchers adds significant weight. In statistical analysis, repeated observation of the same phenomenon by distinct teams reduces the likelihood that the pattern is an artifact of selective reporting or confirmation bias. Each rediscovery converges on the same geodesic, reinforcing that the alignment is not a mere coincidence. While no claim is made that a single civilization orchestrated this arrangement, the pattern persists beyond what random distribution models predict. The Cyclopean Great Circle also challenges assumptions about how early societies perceived their world. Most models of ancient cognition suggest that civilizations were locally focused, constrained by river valleys, mountain ranges, and resource availability. The evidence of repeated Cyclopean sites aligned along a single geodesic implies a conception of Earth that transcends regional familiarity. Even if the builders were unaware of the global network in total, the pattern suggests a shared understanding of orientation, distance, or alignment that operates on a planetary scale. Yet the alignment alone does not construct buildings. Geometry provides the framework, but stone, labor, and architectural knowledge are required to translate lines into monuments. The presence of Cyclopean masonry along a mathematically precise path implies more than abstract awareness. It implies application. Someone, somewhere, understood not only the Earth's curvature, but also how to situate physical structures in accordance with it. The monumental constructions along this circle are evidence that comprehension of planetary scale geometry could be operationalized in practical architecture. This realization forces a profound question. Ancient cultures may have had diverse motivations for building, from religious devotion to social organization. But for multiple sites, spanning continents and separated by thousands of years, to converge along a single mathematically definable great circle, there must have been more than casual placement. The Cyclopean Great Circle suggests an intentionality that transcends individual culture or era, a geometric logic applied consistently to some of the most remarkable structures humanity has ever built. The circle's credibility rests on the combination of architectural evidence, geodesic analysis, and independent confirmation. Each site along the path is remarkable on its own. Together, they form a framework that is statistically improbable and functionally coherent. This network cannot be dismissed as anecdotal or coincidental without ignoring multiple layers of independent evidence. And yet, for all its significance, the Cyclopean Great Circle is still silent. It records no names, no instructions, no overt narrative. It communicates only through placement, orientation, and scale. The pattern itself becomes the message, a geometric signature etched into the planet awaiting interpretation. If geometry alone cannot explain the labor, skill, and ingenuity required to build these monuments, then the question arises inevitably. Who possessed the knowledge of the Earth's shape and scale sufficient to coordinate placement across continents? And how was this knowledge transmitted, applied, and preserved in societies separated by time, language, and geography? In the early 1990s, Jim Allison made a remarkable observation. Independently of any prior research, he noticed that some of humanity's most distant and celebrated ancient sites, the Great Pyramid of Giza, the Nazca lines, Easter Island, Petra, Persepolis, Mohenjo-Daro, Ur, and Angkor Wat all appeared to fall along a single great circle when plotted on a globe. This was not a casual alignment. The deviation across this 16,000-kilometer path measured less than a quarter of a degree. The precision implied by such a correlation immediately raises a question that has long challenged historians and archaeologists alike. Could ancient civilizations have possessed the knowledge and technical ability to measure their world with this level of accuracy? To understand what such an achievement would entail, it is necessary to examine the capabilities of these cultures in terms of surveying and measurement. Take ancient Egypt, for example. The Great Pyramid of Giza is aligned with the cardinal directions, north, south, east, and west, with an error margin of mere arc minutes. This precision predates the magnetic compass and satellite navigation by millennia. It implies the ability to determine true north through astronomical observation. The Egyptians likely used the rising and setting positions of circumpolar stars, such as Kochab and Mizar, in methods that required careful observation over long periods. This process demands patience, accuracy, and a systematic methodology. Similarly, the urban grid of Mohenjo-Daro in the Indus Valley demonstrates sophisticated planning. Streets and buildings follow remarkably straight lines, oriented almost perfectly to cardinal directions. Surveying rods, sight lines, and leveling techniques have been suggested as the tools for achieving such precision. These civilizations understood principles of distance, angle, and alignment without the instruments of modern geodesy. They relied on empirical observation, geometric reasoning, and iterative refinement. Long-distance horizon measurement was another critical technique. Surveyors in the ancient world could determine relative positions over many kilometers by observing natural landmarks and using line-of-sight methods. In China, some pyramidal tombs are aligned with distant mountains. In Egypt, certain temple axes follow the Nile's natural curves while maintaining strict alignment to stellar events. These methods do not require satellites. They require careful observation, repeat measurements, and an awareness of the relationship between Earth's surface and celestial references. It is important to note that geodesy, the science of measuring Earth's size and shape, does not inherently require modern technology. A single culture over centuries could accumulate data sufficient to understand local curvature, distances, and orientation. Techniques such as triangulation allow surveyors to calculate positions with remarkable precision. The limiting factors are time, intent, and the meticulous recording of observations. Ancient peoples may have possessed exactly these qualities. Evidence from multiple civilizations suggests that such capabilities were not isolated. In addition to Egypt and the Indus Valley, Mesoamerican cultures such as the Maya and the builders of Teotihuacan displayed alignment practices that imply knowledge of horizon angles and longitudinal relationships. They understood the motion of the sun, moon, and certain stars, and applied that knowledge consistently in urban and ceremonial layouts. But measuring locally or regionally is only part of the challenge. To plot monuments along a single great circle spanning multiple continents, ancient surveyors would need to conceptualize Earth as a sphere rather than a flat plane. While no direct records indicate that they did, the precision of the placements along the observed Great Circle hints at least an implicit understanding of planetary curvature and proportional distances. It suggests that ancient engineers were capable of creating reference frames and translating them across vast landscapes, a process that is conceptually analogous to modern geodesy. It is essential to differentiate between alignment and measurement. A site may be oriented to sunrise, a river, or a mountain without implying global awareness. Geodesy, in contrast, demands a framework that allows one to reference positions across distances that cannot be surveyed in a single sightline. It requires abstraction, mathematical reasoning, and the capacity to apply consistent units or observational rules across hundreds or thousands of kilometers. The implications of this realization are profound. If ancient civilizations could measure, triangulate, and align with such precision, then many of the arguments dismissing intercontinental geometric correlations as coincidence become weaker. Measurement capability exists independently of cultural interaction. Even isolated civilizations could achieve remarkable spatial understanding if their methods were consistent and sophisticated enough. Yet there is a significant boundary to acknowledge. Measurement alone does not establish a planetary reference frame. One can accurately determine north and map a city, a river, or a mountain, but situating that information in a planetary context, establishing coordinates that are meaningful across oceans and continents, is a far greater challenge. It requires a conceptual leap, recognizing that the Earth is a sphere, that distant points are connected through great circles, and that a geometric system can extend beyond the local horizon. The question then evolves. Ancient peoples clearly had the capacity to measure, observe, and align structures with extraordinary accuracy. They developed techniques that enabled consistency and precision over decades or even centuries. But if they could measure locally and even regionally, could they have also developed the concept of a planetary reference frame? Could they have imagined a sphere, defined points on it, and used geometry to place monuments thousands of kilometers apart along a coherent global path? Measurement is one challenge, tangible and demonstrable through archaeology and astronomy. Planetary reference frames are another. They are abstract, conceptual, and far more difficult to prove. The distinction marks the boundary between what is already understood and what remains deeply mysterious. And so, while Jim Allison's Great Circle suggests an intercontinental pattern, it raises a new, even more profound question. Possessing the skill to measure accurately is extraordinary, but to use that skill to position monuments across continents along a single geodesic, one must adopt a planetary perspective. That perspective and how it might have been achieved becomes the next stage of investigation. Beginning in 2018, a systematic effort was undertaken to examine the orientations of ancient sites on a global scale. The Journal of Scientific Exploration published the first comprehensive survey analyzing over 200 monuments, temples, pyramids, and ceremonial complexes from around the world. The goal was simple but ambitious: to determine whether these sites followed recognizable patterns of alignment to celestial or geographic references. Researchers measured orientations relative to true north, taking care to account for local declination, horizon variation, and seasonal solar and lunar cycles. The findings were intriguing. Approximately 19% of the surveyed sites aligned with the cardinal directions: north, south, east, and west. 9% aligned with the solstices, marking the longest and shortest days of the year. 15% correlated with lunar standstills, which follow an 18.6-year cycle of extreme moon positions. 5% aligned with the geomagnetic pole as it existed at the time of construction, while another 5% pointed toward other distant sites. 4% aligned to zenith sun passages, and 1% faced specific stars. Even with these categories accounted for, about 42% of the sites could not be explained by known astronomical or geographic principles. This initial survey demonstrated the complexity of ancient orientation practices and highlighted a significant anomaly. Nearly half of the sites resisted conventional explanation. While some patterns, such as cardinal or solstice alignments, could be linked to ritual, agricultural, or calendrical purposes, a large portion of the data suggested a deeper, less understood system at work. Over the next 6 years, this effort expanded considerably. In 2024, a presentation at the Altars of the Sun and Moon Conference, organized by the New England Antiquities Research Association to coincide with a total eclipse over Lake Willoughby, Vermont, updated the survey. Researchers analyzed nearly 900 sites, incorporating hundreds of newly documented locations from Africa, the Americas, Asia, Europe, and Oceania. High-resolution satellite imagery and digital tools allowed the team to measure orientations with far greater precision and to apply automated algorithms for pattern recognition. The updated survey refined the initial breakdown. Cardinal alignments remained significant at 19%, solstice orientations were slightly lower at 7%, and lunar standstills were observed in 11% of sites, a surprising increase from the earlier survey. Geomagnetic north orientation, particularly in Chinese and other East Asian sites, accounted for 6%. Across this broader dataset, the most striking observation was the persistence of unexplained orientations. Roughly 70% of sites could not be reconciled with conventional celestial or geographic alignments. The regional breakdown revealed additional nuances. In 6 of the 15 geographic regions studied, lunar alignments occurred more frequently than solar alignments. Some sites appeared to face directions associated with distant, seemingly unrelated monuments. Others seemed oriented in ways that made little sense according to traditional archaeological or astronomical models. The unexplained majority challenged existing assumptions, suggesting that our frame of reference, the way we conceptualize orientation and meaning in ancient architecture, might be incomplete. From a scientific perspective, these anomalies are profoundly important. Thomas Kuhn, in his seminal work, The Structure of Scientific Revolutions, argued that anomalies are often the precursors to paradigm shifts. When data consistently fails to fit established theories, it creates the conditions for new conceptual frameworks to emerge. The persistence of unexplained site orientations invites such a re-evaluation. It is not merely a question of coincidence or error. It signals that the standard models of interpretation may be insufficient to account for a broader, more complex system of knowledge embedded in ancient construction. The survey also emphasizes methodological rigor. Measurements were taken relative to true geographic north using satellite imagery corrected for declination and compared with solstice, lunar, and stellar reference points. Automated tools such as mapping applications and algorithms designed to analyze orientations at scale allowed researchers to handle the expanded dataset while minimizing human error. This makes the persistence of unexplained orientations all the more striking. The patterns cannot easily be dismissed as the product of selective sampling or observational bias. Yet this is precisely the point that keeps the mystery alive. Unexplained does not equate to random. A misalignment with known celestial or geomagnetic targets could indicate that the sites were referenced to a system that is no longer familiar to modern observers. It may imply an alternate frame of reference, one that incorporates geodesic knowledge, planetary curvature, or other parameters beyond the traditional scope of archaeology. By viewing the unexplained alignments not as failure but as evidence of a different paradigm, researchers open the door to questions that extend beyond conventional site studies. Could ancient builders have been working with a global coordinate system? Could there have been an understanding of planetary geometry that guided placement across continents? And if so, what form did that knowledge take, and how was it preserved or transmitted? The Global Alignment Survey, spanning 2018 to 2024, lays the empirical foundation for these questions. It demonstrates conclusively that while some sites conform to known celestial or geographic orientations, the majority remain resistant to traditional interpretation. This resistance is not a gap in methodology. It is a signal that a deeper investigation is warranted. And so the conclusion of this survey does not answer the central question. Instead, it reframes it. If nearly 70% of ancient sites defy conventional explanation, the issue is not random chance, but potentially the choice of frame of reference itself. The coordinates, measurements, and orientations that make sense within modern paradigms may have little relevance to the logic employed by those who built these monuments. Measurement has been documented, patterns have been observed, and anomalies have been quantified. What remains is understanding the reference system in which these anomalies acquire meaning. If unexplained does not mean random, then it points to the next logical step in the investigation. Perhaps the sites were measured and positioned according to a planetary frame of reference that has been lost overlooked or obscured over millennia. The question becomes unavoidable. If ancient builders had precise measurement tools and techniques, and if so many sites remain unexplained, what frame of reference were they using to impose order upon the world? Measuring the orientation of ancient sites is a task that demands both precision and methodological rigor. For centuries, archaeologists relied on compasses and direct field measurements, but these methods are limited by local magnetic variations, human error, and accessibility. A compass alone does not point to true north. It points to magnetic north, which varies depending on location and shifts over time. To account for this, declination correction is applied. Declination is the angle between magnetic north and true geographic north, which can differ by several degrees depending on the region and historical period. Accurate surveys must correct for declination to ensure that recorded orientations reflect true geographic directions rather than the vagaries of magnetism. Credible studies of site alignment, such as those conducted for the Journal of Scientific Exploration surveys, emphasize the importance of these corrections in both fieldwork and analysis. Satellite imagery revolutionized site measurement. With the advent of high-resolution imagery and tools such as Google Earth, it became possible to measure linear features, rectilinear walls, and ceremonial avenues from a stable overhead perspective. The method typically involves using a ruler tool within the software to draw a line along the edge of a structure and read the heading relative to true north. This technique allows researchers to measure large-scale sites that would otherwise require weeks of on-the-ground survey. It also reduces human error by providing a consistent reference frame. Studies published in the Journal of Archaeological Science and related geospatial journals from 2015 onward highlight the increasing reliance on remote sensing and satellite-based measurements for precise orientation analysis. One of the most important innovations in recent years is the development of the Sacred Directions app. This tool automates the measurement and analysis of thousands of sites. By entering the latitude and longitude of a location, the app overlays cardinal directions, solstice lines, lunar standstills, zenith passages, geomagnetic alignments, and lines connecting to other ancient sites. This system allows researchers to systematically assess orientations at a global scale, moving beyond anecdotal or manual observation. Sacred Directions has been used extensively in surveys between 2018 and 2024, including the NERA presentation, providing the capability to analyze nearly 900 sites with consistency and repeatability. Automation is critical for both scale and objectivity. When handling hundreds of locations across multiple continents, manual measurement introduces bias and inconsistency. The app and other algorithmic tools allow for batch processing, statistical validation, and cross-checking of angular deviations. Monte Carlo simulations are often used in conjunction with these measurements to determine the probability of observed alignments occurring by chance. By comparing the measured orientations against randomized distributions, researchers can quantify the statistical significance of observed patterns rather than relying solely on visual or anecdotal interpretation. The combination of declination correction, satellite imagery, and automation provides a rigorous framework that removes much of the subjectivity traditionally associated with alignment studies. These methods allow researchers to identify whether a site is aligned to the sun, moon, stars, geomagnetic pole, or other sites with high confidence. The resulting data forms the backbone of large-scale surveys, such as those covering over 900 sites worldwide, and lends credibility to observations of patterns that might otherwise be dismissed as coincidental. Each method has its own limitations. Compasses can only be used in situ, and historical declination must be estimated based on geomagnetic models. Google Earth measurements depend on image resolution and the clarity of linear features, which can be affected by erosion or vegetation. Automated apps rely on accurate input coordinates and assumptions about reference directions. Researchers mitigate these limitations by cross-verifying results with multiple techniques, including ground surveys, historical maps, and astronomical observations. Peer-reviewed studies in journals like Antiquity and Journal of Geodesy have highlighted the importance of methodological triangulation to strengthen conclusions. The evolution of these methods also demonstrates the scientific rigor applied to site alignment research. Initial observations, such as those made by Jim Allison in the 1990s, were based on coordinate plotting and empirical observation. Modern tools allow these early insights to be tested systematically and at scale, providing a quantitative foundation for claims about global patterns. The development of automated analysis and satellite-based validation has moved the field from anecdotal hypothesis to reproducible science, where statistical probabilities and geospatial modeling underpin conclusions. Yet, while methodology ensures precision, it introduces another challenge. Reference frames themselves are not static. Declination changes over time, tectonic shifts move continents, and even astronomical positions drift due to precession. These dynamics mean that orientation measurements are only as meaningful as the reference point to which they are anchored. If the reference, whether the North Pole, a celestial pole, or a magnetic alignment, moves over time, then the interpretation of a site's orientation becomes more complex. The question of moving reference points sets the stage for the next phase of exploration. Measurement is no longer just a technical exercise. When the frame of reference shifts, previously inexplicable orientations may begin to reveal hidden order. The anomalies documented in the Global Alignment Survey might not be errors, but indicators of a system designed for a planetary perspective that differs from our current coordinates. This recognition points toward a deeper inquiry. What happens when the reference point itself moves, and could ancient civilizations have accounted for such shifts in their monumental planning? The implications extend beyond simple alignment, touching on the very concept of planetary awareness and long-term geodesic knowledge. By the time the Global Alignment Surveys expanded between 2018 and 2024, a surprising trend began to emerge from the data. In multiple geographic regions, more ancient sites were oriented toward the moon than toward the sun. This was not merely a minor anomaly. In 6 of the 15 regions studied, including parts of Mesoamerica, the Levant, and China, lunar standstill alignments outnumbered solar orientations. Traditionally, archaeoastronomers and historians have emphasized solar alignments, solstices, equinoxes, and zenith sun passages, as primary markers for ceremonial, agricultural, or calendrical purposes. The prominence of lunar alignments challenges these conventional assumptions and suggests a more nuanced understanding of ancient astronomical priorities. The phenomenon being measured is known as the lunar standstill, a motion of the moon that follows an 18.6-year cycle. Over this period, the moon reaches its northernmost and southernmost extremes in the sky, producing major and minor standstills. These extremes are predictable, periodic, and highly observable over successive generations. Ancient builders, capable of careful horizon observation, could track these cycles with remarkable precision. Evidence of such awareness is found in sites like Chaco Canyon in New Mexico, where complex alignments correspond to lunar standstills, and at Palatine Hill in Rome, where certain structures similarly reference lunar extremes. Even the ziggurat of Ur in Mesopotamia appears oriented in accordance with lunar standstill positions. The implications of this lunar dominance are multifold. First, it demonstrates that ancient builders were not exclusively focused on solar phenomena, as is often assumed in traditional interpretations. Instead, the moon, with its slower, longer and more complex cycle, may have represented a critical celestial marker for ritual, navigation, or geodetic reference. Tracking the moon over decades would have required sustained observation, record-keeping, and mathematical abstraction, suggesting a level of sophistication in ancient astronomical practice that aligns with the precision required for global alignment of sites. Second, Lunar alignments complicate solar-centric models of orientation and monument placement. While solstice alignments are relatively straightforward, corresponding to the rising or setting sun on particular days, lunar standstills are more subtle. They involve shifts in azimuth over long periods, and their observation requires a more intricate understanding of lunar motion and its interaction with Earth's axial tilt. For civilizations separated by thousands of kilometers and without direct contact, the ability to encode this knowledge into architecture is remarkable and points toward the possibility of shared methods or independent mastery of celestial observation. Research into lunar standstill alignments draws on both archaeoastronomy and geodesy. Modern studies utilize satellite imagery, GIS modeling, and astronomical simulation software to reconstruct horizon positions at the time of construction. For example, studies of Chaco Canyon's lunar observatories, conducted by Anthony Aveni and published in Sky and Telescope and World Archaeology, confirm the intentional alignment of key structures to lunar extremes. Similarly, recent work in East Asia and Europe has mapped lunar standstill directions using high-resolution terrain modeling combined with historical precession calculations, ensuring that measurements account for the changing positions of celestial bodies over millennia. In the context of the main topic, the global geometric network of sacred sites, lunar dominance offers an intriguing connection. If builders were tracking the moon with such precision, it suggests a sophisticated framework for measuring angles, distances, and directions. Lunar observations require long-term consistency, and their incorporation into site orientation implies that ancient engineers were capable of using astronomical reference points to anchor geodesic relationships over vast distances. This ties directly to the question raised by Jim Allison's Great Circle observation: how could civilizations separated by continents and millennia place their monuments along a coherent planetary network? The moon, with its predictable extremes, may have served as one such universal reference. Moreover, the prevalence of lunar alignments raises the possibility that ancient builders were tracking other cyclical or long-term astronomical phenomena that remain underappreciated today. The moon's 18.6-year cycle is just one example of a slow, extended rhythm in the sky. Its use in monument alignment implies an awareness of temporal scales that far exceed individual lifespans, hinting at knowledge systems capable of integrating celestial mechanics with terrestrial geography. Finally, lunar dominance underscores the inadequacy of purely local explanations for site placement. The consistent observation of lunar extremes across continents reinforces the argument that many ancient monuments are part of a broader, coordinated geometric network. The patterns are not random. They reflect deliberate choices informed by careful observation and calculation. Alignments to the moon may have served multiple functions simultaneously: ceremonial, agricultural, calendrical, and geodetic, but they also provide a clue to the underlying principles guiding monument placement at a planetary scale. If the moon mattered more than the sun in multiple regions, then the next question naturally arises: what other celestial, magnetic, or geophysical phenomena might ancient builders have been tracking? Were there additional reference systems, some invisible to us, that informed the positioning of monuments along the global network identified by Allison and others? The evidence of lunar dominance invites us to consider that our understanding of ancient knowledge is incomplete, and that the geometry of the planet itself may have been both the canvas and the ruler for civilizations separated by oceans and centuries. The investigation into lunar alignments thus serves as a bridge between celestial observation and the construction of a planetary geometric framework, suggesting that the global alignment of sacred sites may have been guided not only by mathematics and geography, but also by the rhythms of the moon. Beneath the surface of our planet, invisible forces flow in patterns older than any written record. Telluric currents, natural electrical flows traveling through rock and water, pulse continuously, shaped by molten iron in the Earth's core and by particles streaming from the sun. These are not mystical channels or ley lines of legend. They are measurable physical phenomena governed by the laws of physics, and they leave subtle fingerprints across the crust. Above this hidden circulation, the Earth's magnetic field stretches like a living web. Born in the churning iron of the outer core, it drifts, fluctuates, and bends in response to forces both terrestrial and cosmic. Magnetic poles wander, sometimes tens of kilometers per year. Every location on the planet carries a unique magnetic signature, with a direction, inclination, and intensity that shifts over time. Long before the invention of the compass, ancient builders may have sensed these directions with lodestones, through the careful observation of stars and the horizon, or by meticulous trial and correction. Take the pyramids of Shanxi province in China. Their earthen forms align with remarkable precision to magnetic north as it existed at the time of construction. Modern satellite imagery combined with paleomagnetic reconstructions confirms deviations of only a few degrees. These were not acts of chance. They were deliberate, requiring patience, observation, and a keen understanding of the Earth's subtle movements. One cannot help but ask, how deeply did these cultures comprehend the forces shaping their world? Today, scientists overlay these ancient sites onto high-resolution geomagnetic maps, such as those produced by NASA and the World Digital Magnetic Anomaly Map, known as WDMAM. These maps are derived from decades of measurements collected by ships, aircraft, and satellite missions like the European Space Agency's Swarm constellation. Using advanced mathematical models called spherical harmonics, researchers construct a three-dimensional representation of the magnetic field, producing a vector at every point on the globe, an arrow indicating both direction and intensity. Now imagine this as a narrative exercise. Picture a pyramid in your mind, its central axis stretching outward. Alongside it, imagine an arrow representing the magnetic field at that exact time in history. The critical question is deceptively simple. Do these two arrows point in the same direction? Scientists do not need to see the equation to understand the concept. They visualize alignment, angle, and deviation. A perfectly aligned monument forms a tiny angle with the magnetic vector. Random placement produces angles that could range anywhere from 0 to 90 degrees. By repeating this process across hundreds of monuments on every continent, a pattern begins to emerge, a subtle arm. The results are astonishing. Many sites align far more precisely than chance allows. When these orientations are plotted alongside known great circle alignments, volcanoes, and impact craters, a larger, coherent network emerges. The Earth, in its motion and magnetic complexity, provides a reference frame that seems to have guided ancient builders. The patterns are global, consistent, and precise. Telluric currents add further nuance. Regions of high conductivity in the crust can slightly distort local magnetic readings, creating gradients. By mapping these zones and overlaying ancient sites, researchers find that many monuments appear strategically positioned near these subtle variations. Could it be that builders, perhaps instinctively or through generations of observation, were aware of these electromagnetic nuances? Were they using the Earth itself as a guide, sensing flows and fields that we can now measure but could not fully see? Consider the temporal dimension. The Earth's magnetic field is not fixed. Declination shifts, intensity fluctuates, poles wander. A monument that appears misaligned today may have been perfectly oriented thousands of years ago. Paleomagnetic modeling allows scientists to reconstruct these fields over time, effectively rewinding the clock. Each ancient site, therefore, is not a fixed point, but a moving target relative to a dynamic planet. It is a lesson in deep time, a reminder that Earth is alive, and that knowledge of its rhythms was encoded into stone, earth, and clay.
From a philosophical perspective, this raises profound questions. Were ancient builders aware that the Earth itself was dynamic? Could they track subtle changes over decades, even centuries, maintaining alignment across generations? Were these monuments purely ceremonial, or did they encode an empirical understanding of planetary behavior? a knowledge of geomagnetic flows, currents and vectors.
Could invisible currents have guided the placement of monuments from Egypt to Peru? Did shifting magnetic poles influence the orientation of temples in China and pyramids in the Americas? Were ancient civilizations tapping into a planetary scale grid, a geometry that transcends culture and geography? By translating magnetic vectors into orientation data, scientists today can see patterns previously invisible. They are able to map what may be the threads of a coordinated geometric network, aligning monuments across continents in response to both visible and invisible forces. This approach bridges archaeology and geophysics, linking human ingenuity to planetary dynamics. Imagine standing before a pyramid, a temple, or a Nazca geoglyph, knowing that its orientation encodes the Earth's magnetic field as it existed thousands of years ago. Each structure becomes more than a monument. It is a record, an instrument, a silent dialogue between humans and the planet. And when similar patterns are repeated across continents, the scale of intelligence and observation becomes awe-inspiring. Could the Earth itself have guided our ancestors? Could unseen currents, shifting poles, and magnetic fields have shaped the very geometry of civilization? Each question pulls us deeper into a puzzle spanning oceans, millennia, and cultures. If you find yourself captivated by the hidden geometry of our planet, consider subscribing. The journey has only begun. There are more currents to trace, more vectors to follow, and more secrets hidden in the subtle alignments that stitch together ancient civilizations across the globe. Imagine a world where the North Pole is not where it is today, where the ice, oceans, and continents we take for granted have shifted beneath our feet. This is the central idea of Charles Hapgood's Earth crust displacement hypothesis. Unlike plate tectonics, which describes the slow movement of individual plates over millions of years, Hapgood proposed that the entire outer crust of the Earth could shift, moving as a single unit over the liquid interior. According to Hapgood, these shifts were not random. They could occur suddenly, over hundreds or thousands of years, driven by the redistribution of mass, ice, sediment, or volcanic deposits. The effect would be to move geographic poles hundreds of kilometers, altering climates and shifting the reference frame for any civilizations that existed at the time. What makes this hypothesis relevant to our story of global alignments is that many ancient monuments and sacred sites seem to reference polar positions that no longer exist. Researchers have mapped ancient sites using these hypothetical poles, and astonishingly, patterns emerge. Some of the most famous alignments, including Teotihuacan in Mexico, the Osirian in Upper Egypt, and the Pantheon in Rome, line up almost perfectly with a North Pole positioned in Hudson Bay. This suggests that the builders were using a reference frame that has since moved. Moving further back in time, Hapgood proposed a pole in the Norwegian Sea, approximately 50,000 to 75,000 years ago. Sites such as Chichen Itza in Mexico, the Porbazin fortress in Siberia, and portions of the Nazca lines in Peru show alignment relative to this shifted pole. Earlier still, between 75,000 and 130,000 years ago, the pole may have been near northern Greenland. Sites like the Parthenon in Athens, Baalbek in Lebanon, and parts of the Temple Mount in Jerusalem correspond to this earlier reference. Even more remarkably, the oldest pole position is hypothesized to have been in the Bering Sea more than 130,000 years ago. The orientation of Nazca lines in Peru's Sacred Valley, the Temple of the Sun at Ollantaytambo, and Lion's Rock at Sigiriya in Sri Lanka appear to reference this ancient polar frame. This suggests that the act of alignment was not arbitrary. Builders, separated by continents and millennia, may have been tracking a moving reference point on a dynamic planet. Climate data offers additional support, at least in a correlational sense. Ice cores and sediment analysis suggest abrupt climate shifts corresponding roughly to the timing of Hapgood's proposed pole movements. While the hypothesis remains outside mainstream geology, the correlations are intriguing. Sites that reference these past poles are often located in regions that would have experienced dramatic environmental changes during pole shifts, suggesting that ancient civilizations may have adapted their architecture, orientation, and placement to a planet in flux. Hapgood's hypothesis is controversial because it challenges conventional timelines. If even partially correct, it implies that some civilizations existed far earlier than our current archaeological consensus allows. Structures we attribute to tens of thousands of years ago could in fact predate our understanding of civilization itself. The implications are profound. Perhaps humans were capable of surveying, measuring, and aligning structures with a moving planetary frame long before history records it. Critically, Hapgood's theory remains a hypothesis, not a consensus. Plate tectonics continues to dominate the explanation of Earth's physical changes. Yet the precision of ancient alignments, when modeled against these alternative pole positions, cannot be ignored. Even if crustal displacement occurred only partially, the alignments suggest an advanced understanding of the Earth's geometry, a comprehension of planetary dynamics that challenges our assumptions about the ancients. Philosophically, the idea is unsettling. What if the very coordinates we take as fixed, north, south, east, west, were once fluid? What if monuments, pyramids, and temples were not just aligned to the stars, the sun, or the moon, but to a moving planet itself? Our perception of history becomes less a straight line and more a complex, shifting geometry. The stakes are high. If these pole shifts were real, if ancient civilizations measured and encoded them into architecture, then the accepted timeline of human ingenuity is incomplete. Our story of civilization may be only a fragment of what has been achieved on this dynamic Earth, and yet the evidence is not proof. It is a challenge, a question that invites further study, rigorous measurement, and open inquiry. The alignments exist, the patterns persist, and the climate data correlates, but the mechanism remains speculative. That is the mystery we follow, a hidden planetary geometry recorded in stone, earthen platforms, and sacred spaces across the globe. If Hapgood is correct even in part, then the age and capability of civilization may be far older than we dare imagine. And that brings us to an unsettling question. What other knowledge did ancient peoples possess that has been lost to time? What did they understand about the planet that we are only now beginning to measure? As we trace the alignments of ancient monuments across continents, a pattern emerges that is as unsettling as it is precise. Hundreds of sites remain unexplained by conventional models of solar, lunar, or cardinal orientation. When these unexplained orientations are plotted against hypothetical past pole positions, an extraordinary clustering appears. Sites that once seemed random now align across time and space, as if the Earth itself had been a coordinate system, shifting beneath the hands of long-lost civilizations. Consider Teotihuacan in Mexico. Its grid, perfectly aligned to a pole once located in Hudson Bay, becomes intelligible in a way that modern observers could scarcely imagine. Thousands of kilometers away, the Osirian in Upper Egypt, the Nazca lines in Peru, Baalbek in Lebanon, and the Temple Mount in Jerusalem show similar coherence when projected against alternative poles. Sigiriya in Sri Lanka, an ancient fortress rising from the jungle, also fits within this shifting reference frame. Across continents, across millennia, a hidden logic appears. This is not evidence in itself, but it is compelling. It suggests that civilizations may have existed far earlier than mainstream timelines admit, capable of surveying and measuring with a sophistication that challenges our assumptions. It challenges the very notion of linear progress, the comforting idea that human knowledge and technology have always advanced in a neat chronological sequence. Perhaps ingenuity arises, then vanishes, then re-emerges. Perhaps we are seeing remnants of a deep-time civilization, a society whose understanding of the Earth exceeded what we currently recognize. Yet caution is essential. Clustering around hypothesized poles does not prove anything. It is a signal, a hypothesis, an invitation to investigate further. To confirm such claims, evidence beyond alignment is required. Carbon dating, stratigraphy, material analysis, and paleoclimatic correlation must all support the idea that these sites are as old as the models suggest. To date, few monuments have yielded definitive ages compatible with these extreme timelines. Moreover, the evidence we lack is significant. We have no written records explaining methodology, no instruments preserved that could demonstrate precise geodetic measurement across continents. We do not yet have direct evidence of a global understanding of Earth's geometry. What remains is the pattern itself, mathematical, measurable, and consistent, a silent testament encoded in stone, earth, and geoglyph. Philosophically, this demands humility. We are accustomed to assuming that ancient humans were limited to their immediate environment, that global awareness required satellites or compasses, that monumental alignment could only be accidental or ceremonial. Yet the evidence hints otherwise. It suggests that our ancestors may have perceived the world in ways we no longer comprehend. They may have tracked poles that moved, celestial and geomagnetic vectors that shifted, and incorporated this knowledge into the placement of their most sacred structures. The implications extend beyond archaeology. If deep-time civilizations existed, they may have shaped our world in ways invisible to us, leaving behind a hidden blueprint written in alignment, geometry, and planetary observation. Every unexplained site becomes a clue, a fragment of a story erased from history but preserved in stone and landscape. The Earth itself may carry the record, awaiting interpretation. And yet, mainstream archaeology largely rejects this interpretation. The reasons are practical and philosophical, the evidence is circumstantial, the timelines challenging, and the implications disruptive to established narratives. Scholars are trained to be cautious, to require multiple lines of corroboration. Extraordinary claims require extraordinary proof. Alignment patterns alone, without supporting stratigraphy, artifacts, or records, are insufficient to overturn existing frameworks. But consider the broader question. If the evidence were more complete, if deep-time civilizations had left clearer traces, how would it change our understanding of human history? Would we accept that knowledge, sophistication, and global awareness existed tens of thousands of years ago? Would we see human ingenuity not as a linear trajectory, but as a series of peaks, some of which have been lost to time? We are left with a paradox. The alignments are measurable, undeniable, and compelling. Yet the physical evidence to fully substantiate the age and capabilities of these civilizations is incomplete. Science, in its best form, thrives in this tension between what we observe, what we can measure, and what we can reasonably conclude. It teaches us patience, rigor, and humility in the face of the unknown. For now, the pattern remains a question mark written across the surface of the planet. A series of monuments, pyramids, temples, and geoglyphs, aligned not by mythology, not by coincidence, but by a mathematical logic that challenges our assumptions. It is a call to explore further, to measure, to hypothesize, and to remain open to possibilities that stretch the imagination and defy conventional timelines. The story of deep-time civilization is not settled. It is an invitation to consider that human history may be far deeper and more complex than we imagine. Perhaps these alignments are remnants of knowledge passed down across generations, across forgotten ages, encoded into the very geometry of the Earth. For most of the 20th and 21st century, mainstream archaeology has explained the placement and orientation of ancient monuments through frameworks rooted in cultural behavior, ritual practice, and environmental necessity. These explanations emerge from disciplines such as archaeoastronomy, landscape archaeology, and cultural diffusion, and they have driven decades of fieldwork, excavation, and statistical analysis. They do not dismiss patterns, rather, they interpret them within human cultural contexts grounded in evidence. But when confronted with claims of global great circle clustering that transcends regions, cultures, and epochs, These established models are often pulled in different directions. The tension between conventional explanation and geometric anomaly forces us to ask a deeper question. What do mainstream models actually explain, and where do they fall short? One long-standing lens through which archaeologists view orientation and placement is cultural diffusion. This is the idea that ideas, technologies, and cultural practices spread from one community to another through contact, migration, or trade. Archaeologists use this framework to interpret similarities in pottery styles, construction techniques, and adaptive behaviors across regions. If a certain ritual orientation to the rising sun appears in many sites within a cultural network, diffusion explains that similarity as learned behavior passed between neighboring groups. This model grounds explanations in human interactions, geography, and social exchange rather than in planetary geometry. Closely related is the idea of the ritual landscape. Many societies design sacred spaces in relation to local features, mountains, rivers, or distinctive horizons, because those features have cultural or spiritual significance. In Britain, henges and earthworks are often interpreted as sites of communal ritual rather than precise astronomical observatories. Archaeologists have proposed that these landscapes were shaped by the lived experience of people, including their movements, ceremonies, and cosmologies. This viewpoint emphasizes context, belief systems, and human intention rooted in local experience rather than mathematical abstraction. Another major framework is archaeoastronomy, the study of how ancient structures align with celestial bodies. Scholars like Sir Norman Lockyer in the late 19th and early 20th century made some of the first systematic investigations into megalithic orientations toward the sun and stars. In more recent decades, researchers have used advanced methods, from geographic information systems to statistical analysis, to assess these patterns more rigorously. Sites such as Stonehenge, Nabta Playa in Egypt, and the Sun Temple at Mesa Verde have demonstrated solar and lunar alignments with seasonal or ceremonial significance. In Western Sahara, for example, field measurements of more than 200 dry stone monuments reveal patterns that correspond to solar azimuths and lunar declinations consistent with ritual calendrical needs. This work, published in peer-reviewed journals, shows how communities encoded celestial knowledge into landscape design in a statistically meaningful way. These models are grounded in observable cultural behavior and supported by careful statistical sampling and comparative study. They avoid overclaiming beyond what the evidence can support, but they also show their limits. Astronomical alignment explains why a stone circle might face the winter sunrise, or why a temple axis tracks the rising point of Venus. It does not, however, account for patterns that span multiple continents with remarkable geometric precision, where sites separated by oceans and millennia appear to fall along the same large-scale spherical paths. Another key factor in mainstream critique is pattern-seeking bias. Humans are extraordinarily good at recognizing patterns, even in random distributions. The same cognitive architecture that lets us read faces in clouds also lets us find shapes in the stars and apparent lines across maps. Academic geoarchaeologists like Tom Williamson and Liz Bellamy have shown that when prehistoric sites are densely distributed, straight-line alignments arise at rates expected by statistical chance, unless corrected for multiple comparisons and geographical clustering. Their 1983 work, Ley Lines in Question, demonstrated that many of the straight lines drawn between sites in Britain were not statistically significant once proper methods were applied. This is a foundational critique of line-connecting theories that do not use rigorous sampling protocols or falsifiable predictions. The field of pseudo-archaeology specifically addresses claims that extend beyond what reliable evidence supports. Professional archaeologists such as Colin Renfrew, John R. Cole, Garrett G. Fagan, and Kenneth L. Feder have pointed out that theories lacking empirical support, those that use sensationalist narratives or conflated data types, often rely on fallacious reasoning, selective quoting, or cherry-picked examples that ignore contradictory evidence. These critiques emphasize that rigorous science demands reproducibility, contextual correlation, and multiple lines of evidence, not just geometric coincidence or retrospective line drawing. The classic case of this difference is seen in the study of the Nazca lines themselves. Maria Reiche, a German mathematician and archaeologist, dedicated decades to mapping the Nazca geoglyphs and proposed that many of them served as a giant astronomical calendar. While her documentation and preservation work was crucial, her specific interpretations of celestial intention have been criticized by later researchers such as Gerald Hawkins and Anthony Aveni for lacking statistically significant correlation to the recurring motions of celestial bodies. Today, most scholars acknowledge the cultural importance and ingenuity of the Nazca people, but do not accept the strict astronomical calendar interpretation as definitively proven. Beyond individual site interpretations, mainstream models are robust because they can account for variation and complexity. Archaeoastronomical studies in Mesoamerica, the Mediterranean, and Africa integrate ethnographic records, organic dating, and architectural context to build narratives consistent with material culture. These explanations are multi-layered, grounded in the evidence that archaeologists can excavate, date, and compare, rather than in global abstractions alone. Yet when confronted with claims of global spherical clustering, these well-established frameworks struggle. Ritual landscape design and cultural diffusion operate at regional scales. Archaeoastronomy explains local celestial relationships. Pattern-seeking critiques show how easily humans can overinterpret spatial coincidences. None readily explain why, for example, Giza, Nazca, Petra, Mohenjo-Daro, Easter Island, Angkor Wat, and Tiwanaku might fall within a narrow geometric band on a globe, separated by thousands of kilometers of ocean and cultural discontinuity. That is precisely why proponents of global geometric patterns argue that these conventional theories, while powerful in many domains, leave a gap in the explanatory map when extended to planetary scales. This does not mean the anomalies prove a hidden global civilization or advanced ancient geodesy. It means that anomalies exist, patterns that resist easy fitting into established models. Science advances not by comfort, nor by ignoring outliers, but by confronting them, testing them, and allowing evidence to guide interpretation forward. To understand why mainstream archaeology has been cautious about claims of planetary-scale geometric alignment, we must first recognize a core principle of scientific inquiry. Evidence must consistently outweigh alternative explanations before a paradigm shifts. Archaeologists rely on multiple independent lines of proof, including stratigraphy, radiocarbon dating, material culture, ethnographic context, and spatial analysis. A geometric pattern, no matter how striking, is only one piece of this larger puzzle. For planetary scale alignments to move from anomaly to accepted explanation, they must connect convincingly with other established evidence. The first requirement would be precise dating that correlates with geometric predictions. Many of the sites we examine, from Giza to Mohenjo-Daro to Angkor Wat, already have established dates derived from organic materials, inscriptions, or stratigraphic layers. Yet some of the geometric hypotheses suggest a much older timeline than currently accepted, implying advanced knowledge tens of thousands of years ago. To substantiate this, robust dating techniques are necessary, including calibrated radiocarbon methods, thermoluminescence of ceramics, optically stimulated luminescence of sediments, and dendrochronology where available. Without such verification, claims of extreme antiquity remain speculative. Second, there must be evidence that ancient peoples had the tools and methods to measure and transmit geodetic knowledge. While we know that Egyptian surveyors achieved near-perfect cardinal alignments and Babylonian astronomers recorded precise celestial data, there is no surviving evidence of instruments or techniques that could explain accurate global geodesic placement across oceans and continents. For the geometric hypothesis to gain acceptance, researchers would need to identify either inscriptions, artifacts, or surveying systems that demonstrate the intentional creation of long-distance alignments. Third, the patterns themselves must be statistically reproducible under rigorous scientific methodology. This entails clear criteria for site inclusion, pre-registered hypotheses, independent replication, and the use of Monte Carlo simulations or other null hypothesis tests to determine the likelihood that observed alignments could occur by chance. If multiple independent analyses show that great circle alignments consistently outperform random distributions, the focus shifts from questioning the pattern to asking why it exists.
Fourth, cultural context must explain why monuments were placed where they were. Orientation alone is insufficient. Ancient constructions were embedded in lived human experience, tied to water sources, trade routes, territorial markers, cosmology, and ceremonial practices. A planetary-scale geometric hypothesis must account for these motivations. Why would the builders of the Indus Valley civilization choose locations that align along a great circle with sites in Egypt or Peru? How do such choices relate to their religious, political, or social imperatives? Without plausible cultural grounding, the geometric data risks being interpreted as abstract coincidence rather than meaningful planning.
Fifth, the hypothesis must bridge disciplines. Geometric anomalies intersect archaeology, geophysics, paleomagnetism, archaeoastronomy, and statistical physics. Mainstream acceptance would require collaboration across these fields to validate methods, models, and interpretations. This process mirrors past scientific revolutions. When Alfred Wegener proposed continental drift, he presented fossil distribution, geological similarity, and paleoclimatic evidence, but lacked a physical mechanism. It took decades and the development of plate tectonics to confirm his insights. Similarly, geometric patterns require mechanisms that demonstrate how such alignments could be measured, transmitted, and preserved. Finally, the geometric hypothesis must be assessed against alternative explanations. Cultural diffusion, ritual landscape design, astronomical necessity, and pattern-seeking bias remain plausible in many cases. Stone circles in Britain, for instance, align with solstices and lunar cycles, supported by ethnographic and calendrical evidence. To supplant or complement such explanations, a global geometric model must account not just for orientation, but also for why geographically distant, unconnected cultures would encode similar geometry in ways that conventional models cannot predict. The resistance from mainstream archaeology is therefore not stubbornness, but methodological caution. Extraordinary claims demand extraordinary evidence. Yet anomalies are not obstacles to science. They are its engines. Thomas Kuhn observed that persistent anomalies force science to question assumptions, refine methods, and expand theoretical frameworks. A geometric pattern that withstands rigorous testing, aligns with cultural context, and is independently reproducible becomes a candidate for a new paradigm. To integrate planetary-scale geometric patterns into mainstream archaeology, 5 conditions must be met: precise dating consistent with predictions, evidence of measurement systems, reproducible statistical validation, meaningful cultural context, and interdisciplinary corroboration linking geometry to human behavior. Each of these steps is challenging, but none is beyond the reach of careful research and scientific collaboration. The anomalies themselves are not threats. They are invitations to deepen our understanding of human ingenuity and our ancestors' interaction with the Earth. Science progresses not through comfort, but through confrontation with the unexplained. Each monument, each alignment, each statistical outlier is a question posed by history. If these patterns are real, they reveal civilizations with a mastery of measurement and observation far beyond current assumptions. If they are not, they still challenge us to refine our methods, question our biases, and explore the limits of human understanding. The beauty of science is that curiosity, evidence, and disciplined investigation are enough to embark on the journey. And if this exploration of hidden geometry and planetary patterns ignites your curiosity, subscribing ensures that you will witness each discovery as it unfolds, guiding you deeper into the mysteries etched into the earth by civilizations long past. Long before nations, borders, or empires, the earth existed as a measurable body, a sphere of mountains, rivers, and oceans waiting to be understood. Ancient civilizations, though separated by continents and centuries, treated the landscape not merely as territory, but as a canvas of geometry. Each mountain, valley, and coastline was a reference point, a fixed node in a mental grid that allowed humans to navigate, survive, and communicate across vast distances. This grid was practical first. Knowledge of where to find water, arable land, or trade routes was essential. Mapping the earth was not symbolism, it was survival. Yet within this necessity, something extraordinary emerges. The placement of megastructures from Giza to Mohenjo-Daro, from Angkor Wat to Easter Island, hints at a deeper order, one that transcends local geography or immediate needs. These sites fall along great circles in geodesics, with a precision that defies casual planning. The alignment is so consistent that it suggests an awareness of the Earth as a whole, a planet that could be measured, tracked, and mapped in a universal language of geometry. Before the invention of writing, before the abstraction of numbers as we know them, humans were already encoding spatial knowledge in stone, earth, and placement. Geometry became the first global language, intelligible across cultures that never met, yet somehow responding to the same underlying grid. Mapping was not only practical, it was philosophical. By establishing fixed points and relationships between them, ancient civilizations were engaging in a dialogue with the planet itself. Each monument, each line, each orientation is a question posed to the cosmos. Where are we? How does this place relate to the whole? In this sense, geometry was both tool and philosophy, both survival strategy and contemplative act. The Nazca lines, when read as a planetary map, illustrate this dual purpose vividly. The geoglyphs are not random figures, they are coordinates, markers, and foci in a web of great circles that link continents and civilizations. Through these lines, the Earth was being measured, understood, and mapped long before modern instruments existed. Even modern science confirms the sophistication of these ancient approaches. Satellite imagery, geodesic modeling, and geomagnetic mapping reveal that these alignments are not artifacts of coincidence. They correspond with measurable features of the Earth's surface, from volcanoes to craters, from magnetic anomalies to telluric currents. These are not mystical coincidences. They are reflections of a deep engagement with the planet's physical reality. Ancient humans, through observation, measurement, and perhaps intuition, discovered a blueprint of the Earth that remains largely invisible to us today. The existence of such a blueprint also reframes our understanding of history itself. Civilizations were not isolated, haphazard experiments. They were nodes in a subtle, planet-wide network of observation and placement. The Earth became the canvas upon which humans first expressed global cognition. Geometry was the medium through which knowledge, strategy, and perhaps even philosophy could travel across millennia and continents. The globe was measured not only for survival, but also for comprehension, an early attempt to understand our place within a larger system. Yet for all its evidence, this blueprint remains hidden. It is not written in texts or proclaimed in monuments. It is encoded in the very positions of the structures themselves, in the subtle intersections of great circles, in the consistency of geodesic alignments across oceans and deserts. The evidence requires a perspective that only emerges when the planet is seen as a whole, when maps are interpreted not as local conveniences, but as parts of a unified mathematical design. In this sense, the blueprint is both present and elusive, tangible in its precision, yet intangible in its conceptual understanding. The philosophical implications are profound. If humans once approached the Earth as a measured, knowable entity, what does that say about our own relationship with the planet today? Have we lost the ability to see the underlying order? Were these patterns purely practical, or did they reflect a deeper comprehension of our environment, an early form of global consciousness? The geometry etched into the Earth may not be a relic of lost technology alone. It may be a message, a reminder that knowledge and observation, rigor and creativity can converge to reveal truths that are far larger than any one culture, time or continent. The Earth, measured and mapped in stone and line, becomes more than a world to inhabit. It becomes a text to read, a language written in latitude, longitude and arc. Every alignment, every radial projection, every careful orientation is a phrase in this silent, enduring language. And yet, most of humanity walks across it oblivious, blind to the intricate patterns that link the farthest corners of the planet. The blueprint exists, hidden in plain sight, waiting for the patient observer, the meticulous researcher, the one willing to see not just individual monuments, but the global network they comprise. If this pattern truly exists, it challenges us to rethink what is possible for human understanding, to ask how civilizations could measure, observe, and comprehend the Earth on a planetary scale without modern tools. It compels a reflection on time, patience, and knowledge itself. Perhaps geometry was humanity's first attempt at unifying the world in mind, before it could be unified politically or socially. It was a language written in stone, earth, and alignment, speaking silently across millennia. And it leaves us with a simple yet profound question. If this blueprint exists, why does it feel hidden? Almost as if the Earth itself is whispering its secrets, waiting for us to listen carefully enough to understand. We have traced the lines, measured the angles, and mapped the circles. From Giza to Easter Island, from Nazca to Angkor Wat, we have followed the silent thread that links the monuments of humanity across oceans and continents. We have seen how geometry, observation, and patience could create alignments that surpass chance, forming a planetary network that speaks of knowledge far older and deeper than most scholars acknowledge. Yet all of this, as precise and compelling as it may be, is only the beginning. It is the framework, the scaffold of understanding. The true question lies not in the monuments themselves, but in what they signify about human perception and memory. There is a subtle but profound difference between knowledge and recognition. Knowledge is the collection of facts, measurements, and models. Recognition is the moment when these facts coalesce into understanding, when the mind sees the pattern that has always been present, quietly waiting. We can chart great circles, measure geomagnetic alignments, and project ancient reference frames, yet recognition requires a leap. The acknowledgement that the Earth was once understood as a measured, coherent, and perhaps even sacred object. That our ancestors, separated by oceans and centuries, may have spoken a language of geometry that transcended culture, technology, and time. The implications are humbling. Civilization may not be linear, building inevitably from ignorance to progress. It may be fragile, cyclical, and far older than we have dared to imagine. Entire epochs of observation, knowledge, and craftsmanship could have been lost to time, their traces faint yet enduring in stone, in alignment, and in the very fabric of the Earth itself. These alignments, these great circle networks, remind us that human achievement is not always written in texts or inscriptions. Sometimes it is encoded in placement, in observation, and in geometry, quiet, silent, waiting for those willing to look deeply. And so we arrive at the final, unavoidable contemplation. We have seen the Earth as a measured object, as a canvas of precision and possibility. We have glimpsed the faint traces of civilizations that understood something fundamental about the planet, something we have almost entirely forgotten. What remains is not a solution, not an answer to be filed in textbooks, but a question that reaches beyond archaeology, beyond mathematics, and into the very nature of memory and knowledge itself. If the Earth itself was once mapped as sacred geometry, if its mountains, rivers, and plains were nodes in a network understood by minds long vanished, then what have we forgotten how to read? What messages lie buried in alignment, in great circles, in the quiet, patient work of observation and placement? And if we cannot recognize these messages today, How many truths of our own world, our own history have slipped beyond our comprehension, waiting silently for rediscovery?
Perhaps this is the final lesson of the Earth grid, the cyclopian alignments, and the Nazca map. That knowledge is not only what we measure, but what we see, and that understanding is not merely discovery, but recognition. The monuments stand as monuments not merely to the skill of their builders, but to the capacity of the human mind to perceive order, to measure, and to engage with the world in ways we are only beginning to grasp. The pattern persists, resilient and inscrutable, a silent challenge to us across the millennia.
And so, with every line traced, every circle mapped, every vector compared, we are left not with certainty but with awe. We are left not with answers, but with a question that echoes across continents and centuries. If the Earth itself was once mapped as sacred geometry, what have we forgotten how to read? Thank you for joining us on this extraordinary journey through the universe on frontiers of infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.